So welcome to SoundWaves. This is our 8th SoundWaves event of the year. It's been a pretty big year for SoundWaves. A lot of familiar faces here. Thank you so much for coming back. For those of you who are here for the first time, I hope you enjoy it and learn a lot and become more interested in all the fascinating things that happen in our universe. Tonight, those things have to do with metal and what it is and where it comes from and how we use it. If you'll permit me a little bit of review of the year and of SoundWaves, which is finishing its 2nd year, I want to say a couple of things. Number one, here are the 29 departments that have collaborated on SoundWaves events. Art, astronomy, biochemistry, biostatistics and medical informatics, that's one department. Botany, cardiology, the Center for Complexity and Collective Computation, chemistry, classics, these are in alphabetical order, not order of preference. Communicative disorders, computer science, design studies, engineering, entomology, genetics, geography, geoscience, history of science, a librarian, materials science, mathematics, mechanical engineering, music, of course, neuroscience, physics, plant pathology, psychology, the School of Human Ecology, and veterinary medicine. Additionally, we have had one Nobel Prize winner. I challenge our science faculty, please win some more Nobel Prizes and then come speak at SoundWaves. And this year, the 8 topics that we covered were beauty, groups and their behaviors, color, newness, rhythm, wood, repetition, and now metal. So we've covered really a huge range of stuff with a huge range of scholars, and I'm very proud of that, and I hope our scientists are as well. It's the scientists and humanities speakers. It's the speakers who really make SoundWaves such a fun thing and such a great experience for learning about the world. I just want to mention one other thing, well actually 2 other things. One is that we're having our first ever outreach event for SoundWaves at East High School at the end of May. So that's pretty exciting. We'll be doing a mini SoundWaves presentation for high school kids, math kids and band kids. And next year, our first SoundWaves event will be at the Science Festival, which is in October. I don't have the date off the top of my head, but we will be on the Friday night of the Science Festival. So hopefully a lot of people can come to that, and our theme will be localness. So there's some very interesting stuff being planned. I'm hoping to have someone who can talk, for instance, about fermentation. Very important to Wisconsin. Also next year, we are cooling it a little bit. 8 events is wonderful, but it's a little bit devastating, especially from the email perspective. So next year, we will have 4 events, and I hope to see all of you at as many of those as you would like to come to, and I will certainly be there to greet you. As always, we do not have a Q&A after the lectures because, as I always tell the scientists, if there were a Q&A, we'd never get past the first lecture. However, please, we have a whole museum of interesting things made out of metal up here, so please come up afterwards. All of the scientists are sticking around. They're more than happy to speak with you and answer questions, and you will probably have many. So let us proceed. Thank you so much.
There we go. Excellent. So I hope you can hear me. It's a great pleasure to talk to you today, and I will tell you on a very grand perspective where metals come from, and then the speakers after me will tell you what great things you can do with them. So the title is Metal and Stars, and really it should be more like metal from stars, but there is metal in stars, and I'll tell you where. So this is an image that shows you what the end of the presentation will be. It's a supernova explosion, and all of these different colors show you different metals, and that's what the take-home message of this talk will be. Metals come from supernovae. So if you were to ask what the universe is made of, this would be an appropriate slide. And that's because the universe is made of 73% dark energy, 23% dark matter, and 4% regular stuff, atoms. And these are called dark because neither of those two things emit light, and we can't see them directly. We can study them indirectly. We don't know what they are, and so for the rest of the talk, I will just ignore them. Now, both of them could be a topic for an entire 10-semester class. But I will talk about the remaining 4%, stuff that we are made of, right? So we are the 4%, so to speak. And atoms, right? Where do they come from? And what are they? What is the universe, the atoms in the universe? What is the composition? So if you were to look not at the average piece of universe and ask, what is that? But at the gas in our own galaxy, the Milky Way, then you would get a different answer. So here is the Carina Nebula. It's a star-forming region. It's a gas cloud in the Milky Way taken by the Hubble Space Telescope. And there are lots of young stars forming on this image. And you could ask the question, what is all this gas? What are the atoms in this gas? What's the composition? And then I would say 74% of the atoms are hydrogen, 24% are helium, and the rest, the 2% that are remaining, is everything else. And astronomers call that metals. Now, we lump everything together that is not hydrogen or helium because it's just such a small amount. It really doesn't make sense to make a difference. So I will talk about metals as anything heavier than helium. And the question is, where does it come from? And where does the hydrogen and the helium come from? So the 74% and the 24% are much larger than the 2%, and where do they come from? So here is the cosmic mix in numbers for all the atoms in a pie chart. So here's the hydrogen, there's the helium, and this is the rest. So a lot of oxygen compared to the rest of the stuff, then carbon, neon, iron, and then a smattering of other things. So this is what the gas in the galaxy looks like. This is what the gas inside the sun is made of. Now, here is a periodic table, and I will show two plot-like things today. This is one, and I'm sure you've all seen it before. So here is hydrogen, there's helium, the two lightest elements, and there's all the rest. And we call that metals, right? Now, if you were to ask a chemist, they would say that these things here are the metals, and then these things over here are the other interesting things. But because astronomers don't do much chemistry, we'll go with the astronomer definition. The question is, where do they come from, and where does the helium and the hydrogen come from? So the helium and the hydrogen and a little bit of lithium were made 3 minutes after the Big Bang. It was what we call nucleosynthesis, and these nuclei of the atoms, helium, hydrogen, and lithium, were created 3 minutes after the Big Bang. The conditions were right, and all the helium and all the hydrogen and most of the helium in the universe was made then. The rest was not. The Big Bang did not create all this other stuff. The Big Bang stopped at lithium. So the metals are not from the Big Bang. Where are they coming from then? And that was a question that took a long time to answer, but fortunately it was a question that was impossible to ask for a long time too, because we didn't really know that there was such a thing as the Big Bang or the universe outside of the Milky Way. So where does all the other stuff come from? So before we get to that, just a quick word as to why the Big Bang only made mostly hydrogen and helium and not things like iron. So these are sort of sketches of what an atomic nucleus would look like. They're tiny. So the diameter of an iron atomic nucleus is only 1/1000th of the width of a human hair. And they're made of two kinds of fundamental particles. Protons, positively charged, shown in blue, and neutrons, as the name implies, they're neutral, so they don't have an electric charge. And that makes them behave differently. So the red ones are the neutrons, and an iron nucleus, a stable iron nucleus, is 26 protons and 30 neutrons. And helium has 2 neutrons and 2 protons, and hydrogen only has protons. And the reason that the Big Bang only made helium and hydrogen is that there were 7 hydrogen, or protons, created in the Big Bang for every neutron. If you combine them, you get 3 times as much hydrogen as helium, and there's nothing left over for anything else. So where is all the other stuff coming from then, if it's not the Big Bang? So if you want to make things that are heavier than helium, you have to smash these elementary particles together to make new nuclei. You might think that's easy. For example, if you take a neutron and a proton and you put them together, it's not that hard to make a new nucleus because these two particles don't repel each other. One is neutral, one is positive, that's fine. And once they get very close, there's a very strong force that binds these two particles together. It's called the strong nuclear force, but you have to get them very close. It's easy for a neutron and a proton. It's not so easy for two protons. Now remember, everything is hydrogen or helium, and it's always positively charged. Right? Now we have two positive charges, and so that's much harder. So this process of slamming things together is called fusion. Right? You take two protons, for example, and make a new nucleus, and that fusion process is what you need to do to create heavy elements. So in order to do that, in order to slam two particles together that are positively charged, right? So two protons, or a helium nucleus and a proton, they're positively charged, and the electrostatic force between them, the electric force, is much stronger when they're far apart than the strong nuclear force that binds them when they're in a nucleus. So it's extremely hard to put two protons close together because they're repelling each other very strongly. So what you need to do is you need to force them very close to each other. You need a lot of pressure, and you need to move them very quickly. So that means you need pressure and high temperature. That's what you need to make fusion happen. So where do we have pressure and temperature at such extreme values? You might think maybe in the center of the sun, and you would be right. Right? So the conditions in the center of the sun are perfect for nuclear fusion to occur, to bring two protons, two hydrogen nuclei together and make a new nucleus. And so that's exactly what happens in the sun. And it has to happen in the sun. Why does it have to happen in the sun? So here are the conditions. I said 30 million degrees Fahrenheit. That's the temperature in the center of the sun. And the pressure is 1 billion times higher than the pressure in this room right now. Those are the conditions you need to fuse two protons together. So why does the sun have to fuse protons together in its center? Well, the sun is a pretty massive object. It's 1 million times more massive than the Earth. And that creates a lot of gravity. The sun feels an enormous gravitational force that wants to make it collapse into a tiny black hole. But it doesn't, and that's a good thing. We know that it doesn't because it's out there every day. We can see it. It's stable. And why is it stable? Because it has an energy source in its center. And that energy source provides a lot of pressure, and the pressure pushes against the gravity. Right? So if you've ever carried a child on your back up a steep mountain, you know that there's a lot of pressure that weighs you down, and you have to put a lot of pressure back up to not collapse. And the same thing is happening in the sun. The sun is extremely hot and has a very, very high pressure in the center, and it pushes against the gravity, and that keeps the sun from collapsing. So the sun is stable because of the very, very high pressure. And the reason the pressure is so high is because the temperature and the density are so high. And the temperature is so high because there is a source of energy that heats the center of the sun. And that source of energy is fusion. Now, the sun also radiates, and we all know that because, well, maybe not today, but on a good day, we go outside and it's nice and warm and bright, and that radiation is coming from the sun. It's carrying away heat. So the sun is constantly losing energy by warming us and the rest of the solar system. And something has to replenish that heat, and that's the fusion engine in the center of the sun. So this is the other plot I threatened you with. So here is a plot that shows you how stable a nucleus is and how much energy you can get by fusing two protons or two nuclei together. So on the vertical axis is the energy, and on the bottom axis is how heavy that nucleus is. So this is hydrogen, the lightest. This is helium, the second lightest element. And then there's all the other stuff, all the metals. Now, if you take two nuclei from this curve and put them together, right, you can go from here, you can take two hydrogen and go to either this, and you can take two of those hydrogen atoms, put them together and get a helium. If you go up in this curve, that means you release energy. You've gained energy that you've converted to heat. So going up in this curve releases energy. It's easy to do. Going down in this curve requires energy. So that's not a path that you can use to heat your star. You need to be going up on this curve. That's how you release energy. Fusion only works up. You can't go down. So once you're at the top of this curve, there's no more energy to gain. Right? So you move up this curve from nucleus to nucleus to nucleus. You have to jump over these because you'd have to go down, and it doesn't actually give you energy. So you jump over these all the way to the top of the curve, then you're done. No more energy. If you go that way, you lose energy. You'd be cooling your star. That wouldn't work. So what happens in the star as it goes through its fuel, as it burns this fire in its center. Here is the life of a star about 10 times more massive than the sun. Those kind of stars are more interesting, they do more violent things, and they're better at making metals. So let's talk about this star. All right, this is the same plot I showed you, that I just showed you in the previous slide. We're starting at the bottom, hydrogen. This star is mostly made from hydrogen. Right, so we're down at this curve. We have all the way to go up here to get all that energy from the fusion reactions, from the fuel. So when the star starts out, it's mostly hydrogen and helium, and in the center it's hot enough to fuse, to burn hydrogen, to make helium. Right, 4 hydrogen nuclei give you 1 helium nucleus. So this is happening in the center of the star. It takes about 10 million years for this particular star to burn through all of its hydrogen in the center. So it goes from here to here. Right, now we've converted all the hydrogen in the center to helium. But we're not at the top of this curve, so we're okay, we can go further, right? So when the helium in the center of the star is burned out, all the fuel is gone, the star needs a different energy source. If it didn't have an energy source, it would collapse, right? So we need a different energy source. Now we burn helium. Now we go from helium to carbon. Right? We go further up this curve, and outside of that helium, we have shells of burning hydrogen. That's a little, there's a little burning left, and then just a hydrogen envelope of the star. So the next step is helium burning to make carbon. So now we're at carbon. We've exhausted all the helium in the center of the star. Now it's made of carbon. We have to burn the carbon. And we burn it with fusing it with other atoms. And so burning carbon will take us to neon. Okay, so now we've climbed up to this part of the curve. And so that lasts about 5 years now. Right? There's enough neon in the core of the star to last for 5 years. When that's exhausted, we have a core that's full of oxygen. We can burn that. Right? We get some more energy, so we climb this curve. After the oxygen, we can burn silicon. Right? You can see where this is going. We're almost at the top. Silicon burning lasts about a day in this star. This is a star 10 times more massive than the sun, and there's just enough silicon to burn for 1 day. And now, after silicon, when we burn all the silicon, we reach iron. And iron is at the top of this curve. It's the most stable element. There's no more energy to be gained. So now we have an iron core, but there's no more burning. So the iron stops burning. There's no more energy generation. And the question is, what happens next? Well, that's a good question, and it leads me back to the first slide. But let's take stock and see where we are. At this point, the temperature is about 7 billion degrees Fahrenheit in the center, and it's a pretty extreme object. In this particular star, there is about 1.4 times the mass of the sun in iron in the center. 1.5 times the mass of the sun in this iron core. It's extremely dense. So where are we? Well, we've made elements all the way from hydrogen to iron and a little bit of nickel. So we've done about, a third of the periodic table. So we've created elements, we've created some metals, but we have a bit of a problem. What about all the other good stuff? What about pleasant things like plutonium, uranium, cadmium, lead, all those things? Where do they come from? And second, all this stuff is inside a star. So we want it to be out in the gas where all the other stuff is happening, right? We want to enrich the gas of the galaxy to fill these gas clouds that we observe with the metals that we actually see are inside. Right? So how do the metals get into this gas if it was locked inside a star? So this is where the fate of the star comes in. So here we have our iron core, 1.5 times the mass of the sun, but it's lost its ability to generate energy. So now it can't provide pressure support anymore against this enormous weight of almost 10 times the mass of the sun pushing down on it, right? This is 10 times the mass of the sun, 10 million times the mass of the Earth, pushing down on this little core of iron here. And what happens if you step on a balloon and you pop it? No more pressure support? Well, it collapses. And this is exactly what's going to happen to this iron core. It loses this pressure support, it becomes unstable, it collapses all the way until it is about the size of Madison. So in this particular star, 1.5 times the mass of the sun of iron collapsed to the size of Madison, and in the process, all the nuclei inside the star, all the iron nuclei that made up the iron atoms get smushed together into one single nucleus. A giant nucleus, 10 kilometers in radius, size of Madison, made almost entirely of neutrons. All these elements, all these elementary particles get smushed together, and this is what we call a neutron star. It's the end product of a star that's more massive than about 8 times the mass of the sun. So we've made a neutron star, and a neutron star is stable. It's a quantum object. It's a quantum mechanical object. It's held up by a weird ghostly pressure of particles that should be dead, but they can still hold up the star. Is another completely other topic of a presentation we could be giving here. But this is a stable object. It has a solid surface. It can no longer collapse. This neutron star will be there for a very long time. So that was the iron core in the center. It collapsed. And what about the rest of the stuff that was sitting around it that was held up by the iron core before? It's got to collapse too. Right? So it will collapse on that iron core, and in the process, all the nuclei from the silicon and carbon and oxygen and neon, and also some iron that's in this region, gets bombarded with all the neutrons that are created in this implosion. And so what results are two things. Heavy elements. If you take neutrons and you bombard nuclei with neutrons, you load them up with lots and lots of particles. That's easy because neutrons are neutral. You can just shoot them into the nucleus without any problems. So you've made heavy elements in the process. And then there's a lot of energy that's released that makes the rest of the star, the envelope, explode in a violent supernova explosion. 10 times more energy is released in a few seconds than the sun will radiate in its entire lifetime in this explosion. And most of that energy comes from the gravity of the collapse of this object. So we end up with an object that looks like this. This is an image in X-rays of a supernova explosion that happened about 500 years ago. And in the center, you see a neutron star. That's that ember, the little glowing core that's left over from the star. And all the other colors you see are different chemical elements. So there's silicon, I'll show a slightly different image. There's oxygen over here. And this blue haze is titanium that was recently discovered and published in a very exciting paper. It's the first discovery of titanium in a supernova remnant. And so what have we done? We've created really heavy elements. And here's the proof, titanium. It's really heavy, right? It's heavier than iron. And we've made a giant explosion that transports all these metals that we've created, all these heavy elements, out far, far into the galaxy. How far, you ask? Well, here is an image of a nearby galaxy called M82. It's a famous galaxy. Part of this image was taken here at Wisconsin in the astronomy department. And what you see is a galaxy. This is the galaxy. Smaller than the Milky Way, but it has a disk like the Milky Way does. And all this stuff here, all this blue and red and yellow stuff, it's all gas that's being blown about by lots of supernovae that are blowing up in the center of this galaxy, which is forming stars right now. Remember, a star like that I described only lasts for about 10 million years. Right? So there are lots of stars forming right now. They're blowing up all over the place. They're making lots of metals, and that's what you see over here. All those metals are being blown everywhere. They're enriching the entire galaxy. So how do the metals get from the gas to where we are? Well, I think that's the topic of another talk. But before I step off here, let me just show you very briefly. I've brought you a rock from space. It's not really a rock. This is a piece of iron that is a meteor that came down. It's really heavy, so I'm not going to pass it around here. And it's also quite valuable, so I'll leave it up here. And that's iron that rained down from space, created in a supernova. So I'll leave you with my 2 slides. All the hydrogen in your body was created 3 minutes after the Big Bang. So hydrogen, for example, in H2O. Right? So that part of you came from 3 minutes after the Big Bang. And all the other atoms in your body, including the metals, the real metals, that what chemists call metals, were created in a star, or more likely, in a supernova explosion. So.
See something right away here, and that is that I added a title to my talk. I'm supposed to be telling you about metal and earth, but I decided that the real title should be How the Brass Band Began in the Early Years of Our Solar System. And you can see that I didn't actually tell you my name. I'm Laurel Goodwin from the Department of Geoscience. And I didn't tell you my name because I was so busy finding lovely pictures of metals on Earth. And they're lovely because metals hang out mostly in minerals. So we're thinking here just for a moment about brass, because later tonight, then we're going to hear some brass instruments. And brass is made of copper and zinc. And copper happens to be one of the few metals on Earth that is sometimes found in its native form. But most of the time, if we're mining copper from the Earth, we're mining it from minerals. And the minerals include copper, and the copper, the metal, is stuck to a non-metal, like oxygen or sulfur, or some combination of carbon and oxygen and hydrogen. And you can see these are just a few of the kinds of minerals that we mine to get copper. I've just put one of zinc up here. Sphalerite is the most common one, and that, like these, joins metals and a non-metal. So why is that? Well, this is the periodic table of the elements put together by somebody who's not an astrophysicist. And most of the elements, whoa, I obviously am having trouble with this thing. Okay. Most of the elements that we find on the planet are, in fact, metals. And there are a bunch here, so the metals are all in green. There's a smaller number, shown in orange, they're nonmetals, and a handful that we refer to sometimes as metalloids. They have some properties that are intermediate between metals and nonmetals. So why is it that these metals like to stick with nonmetals to make minerals? Well, I'm not a chemist, and luckily there is actually a chemist following me. But in the simplest terms, then this is because metals like to give away an electron, and nonmetals like to take it. So if I were a metal, and this were a nonmetal, and I kind of came up and said, hey, you want one of my electrons? We can share it, and you can have it most of the time. Then we could create an ionic bond and be pretty happy together. So that's the beginning part of the story of metals on Earth and where they hang out. That's the simplest part. But if I told you only that part, and if I told you that almost all of the minerals on the planet have metals in them, and the only exceptions really are ones that have metalloids, like quartz is silicon and oxygen, then you might say, why don't we have a lot more mines? Where are all the mines? Why aren't we mining all of these things? Well, it's because they're not all in really readily accessible form. So the most common minerals in the Earth's crust are actually feldspars. And feldspars are aluminosilicates. They've got aluminum and silicon in them, and they've got a few other metals stuck in there, potassium and sodium and calcium, to balance the charges out. And it turns out that there are a lot more efficient minerals. If you want to say mine aluminum, then you're much better off looking for aluminum oxides. They're a lot easier to work with. So where do we find those? Well, really, what we're talking about when we're talking about mining is mining things that we call ore deposits. And ore deposits are areas where the minerals that have readily accessible metals, metals that are in oxides or with sulfur that form sulfides, for example, are really concentrated. And the reasons that we have those concentrated in parts of the Earth are the same reasons that we have life on this planet, and the same reason that we have plate tectonics. And it really comes down to a really simple point. Our perfect spot in the solar system, where Earth formed, is really the factor that determines where we get ore deposits. So what do I mean by that? Well, when I first started thinking about talking about this subject, I thought it really comes down to what we sometimes call Goldilocks planets. And Goldilocks planets, and Earth is the prototype Goldilocks planet. It's where everything is just right for life. More specifically, it's a planet that exists in what we call the habitable zone. It's not so close to the sun that it's lost all of its atmosphere and lost all of its water. It's not so far away from its sun that it's so cold that any water on the planet exists only in a frozen form. It's in this perfect position where the temperature is just right to retain water. And the planet has to be just right also. The planet has to be large enough to have a large enough gravitational field to hang on to its atmosphere as the solar system forms. And that's the kind of planet that we live in. But there are other ones. You can talk to Sebastian about that. I'm sure he can tell you lots of wonderful things about them. Okay. So let's just take a really quick look at formation of our solar system. And you've already seen now beautiful pictures of outer space. If you've never spent any time on the NASA website, I really urge you to do so. We weren't around to take pictures of our solar nebula before our solar system formed, so I just picked the picture of my favorite solar nebula. I can't even tell you where this was, but I thought it was lovely. But now you know what's in here. There's a bunch of stuff floating around. It's mostly helium and hydrogen, but there are also some other materials in this. And this is kind of also stolen from NASA, kind of what happened, what we think happened in formation of our solar system, and how we ended up in exactly that right place. So the first part of this story is gravitational collapse of a solar nebula to form a protosun in the very center. And as that collapse starts to take place, then the material starts to spin. And spinning around this protosun causes contraction into a disk that rotates around the equatorial plane of that central sun. And we start to get things differentiating, and cooling in this early stage of solar system formation causes condensation into dust-sized solid particles. But what condenses depends on how close you are to the sun. So the particles that are condensing near the sun in the inner solar system, where we are dominated by silicates and metal compounds. That's why we have the planet that we have. That's why we live on a rocky planet. And as this cooling continues, the particles collide and they clump to form larger and larger bodies. And these collide and accrete to form planetesimals, and then finally to form planets. And we get very different planets. The particles that condensed far from the sun in the outer solar system eventually produce planets that are dominated by gas and ice. And those that condensed in the inner solar system have produced rocky planets like ours. But they've also produced something else that's very special, and that's a rocky planet that has all of the three phases of water: ice and gas and liquid. And it has plate tectonics. And that we can start thinking about by thinking about what the early planet looked like. When Earth first formed, then it was covered by a magma ocean. that accretionary process, slamming all that stuff together, created a tremendous amount of heat. So if you can imagine an ocean of lava, of molten rock, then that's what the surface was covered with. It was crystallizing fairly quickly. And if we look at sort of a cross-section through that early Earth, this is what we think it looked like. The magma ocean was differentiating. The heaviest stuff was dripping downward. So we ended up getting those early metals ponding in places, dripping down, sinking in to form the metallic core. The core of our Earth is dominated by iron and nickel. Surrounding that, we started to crystallize minerals. The mantle of our planet is dominated by silicates. And the lightest elements floated to the top, some of them hitching a ride, joining together with things like silicates, metals joining with silicates to float up toward the surface. Now, one thing that I didn't check here, and I don't know if I can do this, but we're going to try, is whether I could give you, it's not going to let me do it. We're going to have to go back here. I didn't check. I did have a little video of this right here. This is not a magma ocean. It's a little crater-filling magma. And what you can see are these areas that are molten rock. And in between are islands of crystallizing silicates. And these form, and then they die. So if we could watch this movie, then parts of these little plates, if you like, protoplates, could move apart from one another, and they could move together. And they move very much like the plates on our planet, but on a much faster time scale. So let's think about what happens if we have something like that, and we start moving things around on our planet. And I want to talk about how that actually ends up concentrating some of the minerals and metals that we like to mine, that we get ores from. So what we're going to talk about is a particularly special place, the Keweenaw Peninsula of Michigan, which happens to be host to the largest native copper deposit that has been discovered on the planet. And what we're thinking about over here is an early stage of our planet where the continents were much smaller than they are today. And at this particular stage in time, more than 1 billion years ago, they were all stuck together in a supercontinent that we refer to as Rodinia. This is the beginning of the North American continent. This will become Hudson Bay. If you can imagine part of North America lying on its side, we're about in here. You recognize some of these other versions of, older versions of continents like Australia. Here's part of Siberia and part of China. And what was happening in this particular location was driven by the fact that all of these continents were stuck together. In periods of time in the past where we've had supercontinents, then they act like an insulating plate above the hotter mantle, and things start to heat up underneath. And it drives formation of what we refer to as mantle plumes, big regions of hot magma that come up underneath these large continents and poke through to the surface and try to tear these larger continents apart. And that's what happened in this region of, right in our backyard of the Midwest about 1 billion years ago. The formation of the mid-continental rift, where the continent was nearly torn apart along these arms. So the gray in here is areas where that deep mantle plume caused molten rock to come to the surface and be deposited as lava flows in the rift. The green in here is areas where sediments were deposited as this rift started to form. The closest analog we have today is the active East African rift. And this is an area where the continents have rifted apart in two arms of the rift already. Here's the Red Sea and the Gulf of Aden are two areas that have been rifted apart. The East African Rift Valley is more similar to what we see here. It hasn't actually torn Africa apart, but there's deep upwelling material from the mantle heating this from underneath. And eventually that will cause it to tear apart. So what happens in these areas? As this magma is driving upward, it heats things up. And it also, as magma, as molten rock comes up and crystallizes, it releases fluids. The heat of the magma, the fluids coming off the magma, and fluids that begin circulating above it, groundwater circulating above it, can actually dissolve metals from the rocks and reprecipitate them. So this is a region where hydrothermal fluids, or hot water in some cases, in other cases these are supercritical fluids, they're something between hot water and a gas. And these dissolve copper from these lava flows and transport it into fractures and into the areas between the grains of the sediment that filled this rift. And in the Kimonon Peninsula, in this particular area, they deposited pure native copper that's now exposed in that region. If you want to see some of these, if you want to see this copper and some of the other copper minerals from this region, then we have some here from the Geology Museum. We also have some materials from other areas, from different tectonic environments, in which the plates are interacting and magma and fluids are concentrating ores into economically viable deposits, the things that we mine. So I'll invite you up to take a look at these, and I'll hand the podium over to our chemist, Judith Burston.
Well, good evening. We're now going to take a significant jump because I'm not going to talk about anything about where the metals came from, but I'm going to tell you a little bit about what they do. And in particular, I'm going to focus in on what they do in us. So, how many of you are aware that you need to eat metals? Okay, there's a goodly number. And what metals can you think of that you know you need to eat? Iron. Okay, most everyone knows iron. Others? I think. Excellent. So, iron was the first one. Pretty much everyone knows iron is an important mineral that we need to eat. Cobalt? Nobody, I didn't think I heard cobalt. You need a teeny bit of cobalt, but it's super important. I heard calcium. Most of us know we need calcium. Zinc. I don't know if I heard zinc. Zinc is another. Copper. I'll say a little bit about copper. Potassium. Molybdenum. Okay. This is just a selection of the elements, metallic elements that we need to eat. And these are components of what we call the mineral nutrients. So what I really want to focus in on is a little bit about what metals do in living things And I'm very grateful to some of the introduction, which helps me to, now you know where they come from, let's look at what we do with them and how we assimilate metals. So living organisms collect or sequester metals from their environment. And we do this by eating, but all living organisms collect metals from the environment. And in general, the elements that we call essential, that is those that we need in order to survive, are the lightest and most abundant elements. So I'm just giving you an example in this table. I have just a little bit of a table to show you how much more concentrated these metals are in us. This happens to be in our blood plasma, which is the liquid in which our blood cells float. And look at how much iron there is in our blood plasma compared to the ocean. And iron, copper, and zinc, you'll notice we concentrate in our blood at much, much higher levels than it is present in seawater. Notice, though, here I said cobalt. Cobalt is essential. We need cobalt, but cobalt is an example of an element where we actually have much less in us than there is in seawater. Most other elements, we have more of the metallic elements. So what I want to just introduce you to, Sebastian started out this talk mentioning that most of the universe is nonmetals. He calls nonmetals hydrogen and helium. I'm going to define them a little bit differently. And now I'm going to look at what the percentages are of different elements in us. So if we look at 99% of the atoms in our body are a really limited number of elements: hydrogen, oxygen, carbon, and nitrogen. And I point out to you, these are the lightest and most abundant elements. And those were really low or relatively early in that constellation of elements as they were forming in stars. About 1%, well, it's a little bit less because we're going to see this. We're going to get to the 0.1% in a moment. So here's the 0.09%, are a group of elements, 4 of which are metals. So calcium, sodium, potassium, and magnesium, but also phosphorus, sulfur, and chlorine. And these are important, but they're less abundant. And I also want to point out to you that this is kind of a little bit unique for people or for mammals because calcium and phosphorus are so large in us because that's a very significant component of our bones. Our bones are made of calcium phosphate mineral. And so for us, calcium and phosphorus are really large. But if you go, for example, to a tree does not have abundant calcium and phosphorus in the way that we do. But this is us. So now we've dealt with 99.9% of us, and we call these the constitutive elements. They're the things that make up the vast majority of us. But as far as I'm concerned, these are the least interesting elements. The ones I care most about are what we call the trace essential elements. And so these are the remaining 0.1% of the atoms in the human body. Now these atoms include the vast majority of the metals. And so what I'm really going to focus on in what I'm going to tell you about are the trace essential elements, and particularly the trace metals. So what's the definition of a trace essential element? And there's basically 3 requirements. If you don't get enough of a trace essential element, you're going to get a disease. And you may be familiar with the most common deficiency in trace essential elements, and that's iron deficiency anemia. There's also another form of anemia called pernicious anemia, and that's when you don't get enough cobalt. And very specifically, you don't get enough vitamin B12, which is the physiologically important form in which you need cobalt. And so that's another deficiency disease. And, oops. Nope, I want to go backwards. So the other thing about these deficiencies is that in order for this to be a real trace essential element, you have to reverse the deficiency. So whatever disease you have, you can reverse it just by adding that element back in the diet. And then those of us who study these kinds of things have a further requirement, which is that we absolutely have to understand what it is that this element is doing in the body. We have to know what its biochemical function is in order for us to say that it's a trace essential element. And you may notice if you look on your vitamins, like some elements will be there. Boron is one, chromium is another, where it's there, but there's no USRDA assigned to it, and that's because it's not been demonstrated that it is a trace essential element, not because we don't know that you need it, but because we don't exactly know the details of what it's doing. And people in my field, biological inorganic chemists, actually study what these various elements do. So here's my edition of the periodic table. Everyone's showing a periodic table tonight. I'm very proud of this, and I thought I didn't bring my pocket periodic tables to give out. I apologize. So this is a little bit more of a in-depth look at the periodic table. I haven't differentiating it according to what's a metal and what's not, but instead according to how much of the element is in your body. So the most abundant elements are in red. That's the hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus. Those are the most abundant. And we could also include calcium. Calcium's also pretty abundant, but in terms of total abundant atom numbers, these guys are coming first. And then there's the still pretty large amounts, the blue guys. That's the sodium, magnesium, potassium, calcium, and chlorine. And then we've got the trace essential elements, the ones that are in pretty large amounts, iron, copper, and zinc, and then the ones that are in super small amounts, like chromium, molybdenum, manganese, cobalt. And there's some nonmetals in here too, fluorine, selenium, and iodine. I want to focus on the blue and the green, and especially these metallic elements and their roles. So I'm going to just tell you a couple of stories, although first I'm going to tell you one more thing about mineral nutrients, and especially the metals. And one of the things about mineral nutrients is that not enough is good, not good, but too much is not good either. And so almost all of these elements, what we find is there's a region of benefit. Think of this as you're great, healthy, happy, and then there's a region of detriment, you're sick. And too little of the element, so if the amount of it, or the concentration in your body is too low, then you're going to be sick and you're going to have a deficiency disease. There's going to be a range where you're perfectly healthy, but if you get too much of most of these elements, especially your metals, they're really quite toxic. And so your goal is always to ingest the ideal amount of these elements. And so your mother will tell you, eat up your steak, whatever it is, so that you make sure you get your iron. But I will tell you there's a disease called iron overload, which is when you get too much iron. And so you have to be careful. You want just enough, not too much. So I'm going to tell you just a few stories about these elements and what they do from a somewhat chemical perspective, but now looking a little bit more detail, what do they actually do in our bodies? So the first thing I'm going to tell you about is that metals turn out to be really involved in the way our bodies use really small molecule gases. So nitric oxide, carbon monoxide, oxygen, and also ethylene are very, very small gaseous molecules, and these molecules are really important to living things. You probably know that oxygen is your cell's energy source. That's why you need to breathe it in, and so you need to get oxygen. If you don't have oxygen, you will die very quickly. Turns out carbon monoxide is made in your body. It's a poison, and there's reasonably large amounts of it under any circumstances, but extremely small amounts seem to be used to help you learn. Nitric oxide, another poisonous gas, if present in large quantities, but in the extremely small quantities that your body makes it, it regulates your blood pressure. Ethylene, plants use ethylene as a developmental signal, and it helps fruits grow, plants grow and fruits ripen. So Some of you may know to put your apples in a plastic bag, paper bag, actually better. Plastic, and not so good. And that will help your apples to ripen. These are really, really simple molecules. So simple that the kinds of normal ways that biological systems use to differentiate molecules don't work, because they're basically the same shape and size. They do have different atoms to give different chemical properties, but it turns out it's not so easy to differentiate them even on the basis of these chemical properties unless you're a metal. And the whole way in which biological systems recognize these little gases is to use metals, because metals are super good at binding to and differentiating these gases. And every single one of these gases is going to be working as a messenger in cells. One of the key ways in which these gases are recognized is through a really beautiful molecule, my favorite molecule, called heme. This is a large organic molecule, but in its center, so it's made up of mostly carbons, the white, nitrogens, the blue, some oxygens, the reds over here, but that red one is the key. That's the iron. And this molecule is the pigment that makes your blood red. These molecules can be anything between red, purple, green. They're very, very beautiful. And the oxygen really likes to attach itself to the iron in the center of this molecule. So does carbon monoxide. And that's in fact why carbon monoxide is toxic, because I'm going to show you a little bit about how oxygen binds to this iron in your blood, in hemoglobin, a protein that carries the oxygen in your blood, carries it from your lungs all the way to the rest of your body. But if you breathe carbon monoxide, the carbon monoxide will bind to the hemoglobin, and then the oxygen can't get to your body, and then your cells will die. So here's a picture of the hemoglobin protein. And these kind of stringy business, these are the chains of amino acids, which are the components of protein. And I'm not going to focus very much on this part of the protein, except to say that there's 4 long chains in this protein. They're curled up in very special shapes, and each one of them has within it one of these heme molecules. Each one of these hemes has one iron inside it. And this large, really huge molecule can bind precisely 4 oxygen atoms, 4 oxygen molecules, one to each of those irons in the heme. And this is the protein that carries oxygen in your blood cells. I want to focus in really close on what that iron does. So this is a side-on view of my heme molecule. Let me backtrack for a second. It's a big flat molecule. So think of it like a dinner plate with an iron in the middle. And what I have here is looking at it from the side. Here's the iron. And the iron is attached to the rest of the protein. These are like those squiggly chains. Here's the iron without the oxygen. It's kind of bent down, and the protein's kind of pulling on it. And when oxygen binds, the oxygen attaches itself directly to the iron. It also gets a little help from this other part of the protein. Oops, it sounds like the thing just cut out. Now it came back. But when the oxygen binds, it pulls the iron and this heme and changes the shape of this immediate part of the heme molecule, and that pulls on this part of the protein, and the whole protein changes shape. What this does is it turns out that when the protein looks like this, it binds oxygen really tightly. When it looks like this, it gives up the oxygen. And so the shape of the protein is linked to whether the protein has oxygen bound or oxygen not. It only takes one of the 4 molecules to start the shape change. So if you bind one oxygen, all of a sudden you combine the next 3 really well. And that helps your hemoglobin take up oxygen in your lungs. When it gets to your muscles and there's not so much oxygen, it gives up one, starts to change the shape back, and gives up the rest of them. And so that really helps your body to efficiently deliver oxygen from your lungs to your muscles. I should also say there's another protein in your muscles that makes your muscles red that is almost like this, doesn't have the 4 of these guys. Instead, it's like one of them. And that's what takes the oxygen from your blood and stores it in your muscles for when you need to use it. There's other proteins in your body that I call gas sensors. And these are the guys that are going to be responsive to carbon monoxide and nitric oxide and are going to help you learn or regulate your blood pressure. And they usually also contain a metal. And there's many of these different kinds of proteins. Sometimes the metal's iron in a heme, sometimes it's iron in another form, and sometimes it's copper. So for example, in plants, the ethylene receptor has copper. And the gas molecule is going to attach to the metal, and the protein's going to change shape, just like hemoglobin, all the same idea. When these proteins change shape, they often do something new and different. And that's why we call it a sensor, because it's going to respond to the presence of the little gas molecule and then do something that is functionally important, like regulate your blood pressure. So here's an example of a carbon monoxide sensor. This is actually from a bacterium that lives in the lakes. It's purple, and this bacterium uses carbon monoxide as its energy source, just like we use oxygen. And it needs to know if there's carbon monoxide available. That's what the purpose of the sensor protein I'll tell you about is. This sensor protein works kind of just like hemoglobin, a little bit differently. It has 2 things bound to the iron in its heme, has a heme just like hemoglobin. Carbon monoxide comes along and knocks off one of these guys, and now you've got carbon monoxide bound. Nothing happens on this side. It doesn't move, but you have to keep this part anchored because you need this to get released and you need this part to stay anchored. And again, the protein's going to change shape. And once the carbon monoxide binds and the protein changes shape, that tells the bacterium that there's carbon monoxide for it to live on. Here's nitric oxide. Nitric oxide regulates your blood pressure. And it causes your blood vessels to relax, making your blood flow more easily. And there's certain drugs that release nitric oxide. One of them's nitroglycerin. If you've ever had a heart attack or angina, you may be prescribed nitroglycerin so that as soon as you feel heart pain, you will put this under your tongue and then it will release nitric oxide, and that will allow your blood pressure to go down. Alfred Nobel is the guy who discovered nitroglycerin. Well, he discovered how to stabilize nitroglycerin. Nitroglycerin is highly explosive, and he made a fortune stabilizing this molecule in the form of dynamite, and he used his fortune to create the Nobel Prizes. But the most ironic thing about his life, he got angina. And it was through his factories that it was actually recognized that nitroglycerin was, had the property of relaxing blood vessels. And late in his life, he said that it was an irony of fate that he had to ingest this stuff in order to control his angina. So that's the end of what I have to say. And I would invite you, I've brought some things that have nothing to do with biology, but some things about isolating metals from ores, an experiment that we do with students in our introductory inorganic chemistry class, and I would invite you to come up and look at that later.
I do not have any slides, but I have show and tell items. My students like those. My name's Jay Samuel. I teach in material science and mechanical engineering. This is all about music, right? What do you think my favorite instrument is? I bought it here. I can play it too. This is going to be our feature for your homework assignment later. It's an old pipe organ, has to be at least 100 years old. But first day of class, I always ask my students, what is the most engineered thing you have in your dorm room or apartment? What do you think it is? More engineering went into that beverage can than Chrysler put in their cars. Maybe you shouldn't pick on Chrysler, but a lot of engineering here. How many do we make of these every year? A lot. Any idea? Yeah, Julian's pretty close. Enough for 4 dozen about for everyone on the planet. So we manufacture 300 billion a year. That's billion with a B. These are made in about 1/5 of a second. Okay, and they're generally made at the canning plant. So I guess Wisconsin's big on beer for definite reason. But if you go take the Miller tour in Milwaukee, you'll see the cans being made right there. And the reason I brought the can in is that the can here, okay, and all those instruments over there are made basically the same way. And the alloys that are used for the instruments and the soda can have certain similarities as well. Thickness of the outside here is about 4 sheets of paper. Okay, there's 2 alloys, one for the body of the can, and so it can survive the opening, we have a different alloy for the top. It's still based on aluminum, but a different, stronger alloy. And this starts out life, okay, as sheet metal. So be rolled flat at the aluminum mill. And then it's deformed into that shape, and that's done with the musical instruments as well. What alloys make good musical instruments? Not all of them do. Let's see what else we got here. Material science, as I said, begins in the kitchen. More accidents at home occur in the kitchen than any other place. So this is stainless steel, selected for its corrosion resistance. Doesn't sound too bad. Cast iron. Okay, these differ in, someone mentioned the word phase before. So we have phases in solids as well. And the best way I can sort of describe that to you is when I was a kid, my mother made Jell-O all the time. And just Jell-O by itself would be a single phase alloy. But if I add fruit to the Jell-O, I now have a multi-phase alloy. Okay, multi-phase alloy, Jell-O with fruit in it. Plain Jell-O. But the plain Jell-O makes the best instruments. There's a good reason for that. Am I going to tell you what that is? Yeah, I guess I'm going to tell you. Metals do something when you hit them with, say, the mallet here. Good analogy is your microwave oven. Okay, that has a certain frequency to the radiation that makes the water molecules dance around. And when they dance around, they get hot and they give off heat. Okay, metals, same thing. Okay, when they're struck, okay, it's not the same frequency or wavelength of the microwave. Don't put your instrument in the microwave either. But they use sound, and they actually do something inside. So, none of you have ever seen this. Ordinary aluminum. Okay, that would be the stuff of the beverage can. And I'm going to take that, I'm not going to be nice to it, I'm going to immerse it in boiling sodium hydroxide. And I get that. Now, this has been treated specially. Normally you wouldn't be able to see those, they're called grains. Okay, and normally you would need a light microscope to see that. But I can grow the grains until they get really large. We got some big large one up at the center there. It's sort of like a bubble bath. When you first hop in the bubble bath, there's a lot of really small bubbles floating around. But after you've sat in there for half an hour, very few large bubbles. Same thing with alloys. So the grains themselves tell me as a metallurgist what has happened to that particular sample, okay, and what its properties might be. That's why when we have, unfortunately, air disasters, that's the first thing that's done with wreckage. Be looked at under the microscope. You can tell where the failure started. You can tell what the likely cause was. But anyway, I have a few photographs I want to show you because, just like my aluminum can here, it starts off as the sheet metal. But if I take that sheet metal and pull on it, okay, I can break it with about 5,000 pounds per square inch. Pressure, stress. But, believe it or not, when this is loaded with soda, 10,000 pounds per square inch, okay, on the external walls here. So, during the forming process, the strength of this actually changes. So I have some what are called microstructures, and they are brass. You can see the individual grains in there. And what I've done with this sample was roll it. And you can see the grains, they start to elongate. Let's see, I think this is, there we go. See some of these grains here? The rolling direction was in that sense. So it's going through a set of rollers. Okay, each set of rollers, it gets thinner. Okay, it also gets longer as well. And it speeds up as well. Okay, but let's take it one step further. Okay, elongation of the grains, and they're actually becoming stronger. So as I do this, the strength goes up, so that with my beverage can, if I start off at 5,000 psi for the strength, okay, how's that going to hold the soda with 10,000 psi? Okay, it actually goes up to about 30,000 psi strength, okay, as a result of the forming process. Same thing would happen with those musical instruments. Okay, later stage during rolling has a texture to it. And this is the last stage. You can't do this too many times or it will break, because in addition to getting stronger, it's also losing its ability to deform without breaking. Okay, and that's a much later stage of deformation. Can barely make out the individual grains here. There's one right there. And here it is with the full thickness of the sheet. Okay, there's one side, there's the other side. So you're looking at a cross section of the sheet. Now, like a lot of things in nature, okay, we work in cycles. So that drives the strength up. I can also take that and put it in the furnace. Say maybe it involves both temperature and time, maybe around 500 degrees Fahrenheit for 20 minutes, half an hour. And that happens. Okay, along with that change in what's called the microstructure, the properties are returning to their original low strength, okay, and high ductility. It can be stretched. That's how we make wire. Start off with bar stock, might be an inch in diameter, and it gets pulled down to the final size of the wire. But to be able to do that without breaking the wire, we need what's called ductility. So, with those musical instruments over there, probably a combination of the strengthening process, which would occur automatically as those instruments are shaped, and depending who's manufacturing, okay, there might be, this is called annealing, okay, to reduce the strength, increase the ductility so that further shaping can take place. So there's a lot in common with my aluminum can and the alloys that are used in musical instruments. Okay, most all of that, I'd bet the ranch is brass. Often it gets plated. Nickel, right? Okay, what was the other alloy? Silver? Okay, nickel and silver. Okay, there's no silver in nickel silver, so don't get excited. How about my final show and tell piece here? When were the first pipe organs manufactured? There's still one in Switzerland that was assembled in 1454, and it still operates. Probably had a few overhauls, but still running. So the great cathedrals of Europe all required these massive pipe organs. So what stuff did they have back then? No iron, unfortunately. Steel came in around 1863 or thereabouts. So what are we going to use for our pipe organ? Yeah, we could use copper. Copper was around at the time. Lead and tin. Okay, and that's what this is made out of. And back then, how'd they get it into the shape? That's the thing that's remarkable. There were no rolling mills back then, like for my aluminum can there. Yeah, there's probably a bit of hammering that would go on. Okay, that would change the strength. Okay, just like that would increase the strength, just like rolling would. It has something to do with heat, a lot to do with heat. Okay, you've done some electrical soldering. This is the same stuff. So that means fairly low melting point. So they actually cast it into sheet by pouring it on a marble slab. Okay, it'd be like making a pizza. So you pound out the dough there and cut things out, roll it, and this has all been hand soldered here. So that's how I know it's fairly old. That's how all the pipe organ stuff was made. They had wood. Some of the pipes were wood. Okay, but no iron back then. couldn't work copper very well. That takes about 2,000 degrees Fahrenheit. So that's a pretty high melting point for a metal. And last thing I'm going to tell you is that a few of our speakers did mention aluminum. And of course, the aluminum recycling has been a very big story. And the key to any recycling process is you have to keep your alloys separate. So the top of that can is mostly aluminum with a few % of magnesium and silicon. Okay, the body of the can is mostly aluminum with a few % of manganese. That helps it roll into a nice, smooth shape. So, how are we going to separate those two? Someone came up with a great idea. Wish I'd come up with it. I wouldn't be here. I think I heard it. Melting point. So they shred up the cans, 2-stage furnace, okay, mesh belt. Okay, first furnace, our body of the can melts through the belt. Okay, and in the second furnace, it's about 100 degrees hotter, and the top melts. So that's how the two alloys are separated, and it's a good thing too, because the chief ore of aluminum is bauxite, and it's an oxide of aluminum, but rather different than most metals. It takes an enormous amount of energy to win the aluminum from the oxygen. They don't like to be separated. So big energy cost, okay, and manufacture what's called primary or new aluminum. But recycling worked out very well for the aluminum. And there's a very famous piece of aluminum. Aluminum's a relatively new metal. Okay, the problem was getting it away from the ore. And there's a very famous piece. Anyone know where it's located? Washington, wow. Washington Monument for sure. So the capstone of the Washington Monument is a chunk of a soda can.
I'm going to use this mic because if I play my horn with the other mic on, I can't step away from it, and it's going to be really annoying. So if my brass colleagues could come up, we need to reshuffle things to make a little bit of room, and I can start telling you about brass instruments, and then we can play. Okay, hello. Brass instruments are all the same. They work all in the same way. They look very different. So when that tuba comes over and the trombone comes out of the case, you're going to say that that's not possible. But I want to show you exactly how they work, how we play them, and why we play them. Let's start with why we play them. Why do these instruments exist? Why do we have them in our orchestras? Answer, basically, because they are loud. The instruments were developed out of animal horns, which is why they're called horns. And they were used to call across a distance because they are louder than the human voice. It turns out if you make them out of metal, they are even louder. Of course, nowadays, composers don't just write for the instruments to play loudly. We have to learn how to control them, play them softly, loudly, and everything in between. By the way, we refer to those volume levels in music as dynamics. So we have to play dynamics with these instruments, but they're great at playing loud. I want to show you how they are similar, and the trombone, which has some more visible parts, is a great way to begin. So that's the trombone, and its hallmark, of course, is the slide, which is there. Now, the instruments are made entirely, well, 99.999% out of metal. The French horn has a little bit of kind of rubber bumpers and some string on it, but basically these instruments they're made out of metal entirely. So when you have a piece of metal moving across another piece of metal, of course you need lubricants, and so the technology of making the instruments has also gone hand in hand with the technology of making the moving parts work, so that now the slide of the trombone moves with just the most wonderful ease, and he doesn't have to work at all to move it, unless he has to catch it when it goes off the end. So the reason I want to start with the trombone is if I ask Mark to play any note, and just play any note. Thank you. Now, if he moves the slide out a certain amount, which he knows because he's memorized it, to go down just a half step. So that musical distance is called a half step. Anytime he moves the slide from wherever it is, that distance, the note goes down by that same amount. So he could play a different note. And he can, and he can play a note that starts out in, say, third position, and then move out the same distance, and there it is. It doesn't matter where he is. By the way, we're all going to be buying a little bit of warm-up time as we do this, so we got a little bit of shenanigans working. Right. So now, in what way do the French horn and the tuba? By the way, I'm going to, if it's okay, call the French horn the horn, even though they're all horns. We usually call the French horn the horn. So how does the horn do that same thing, and how does the tuba do it? And this is kind of a little bit counterintuitive. So we have valves, which are the buttons I'm pushing here with my left hand. And you can see that there are 1, 2, 3 of them here. And what the valves do, and the tuba has actually 4, and I actually have in total 5. I have on this horn, and you have 5 too. We have little extra ones. That's modern technology, and I'll tell you about that in a minute. But the second valve here, the one in the middle, does the same thing. What it does is it opens up this length of tube. Here it is. And it adds that much tubing to my horn. So when I push my second valve, it does the same thing. Now, the tuba is much lower, so his second valve, if you can take it out, is a lot longer.
Texas, everything is bigger. But not smarter.
So you'll notice, it's probably a little bit hard to see, but the width of the tubing on the tuba is also substantially bigger. You can see that in the bells. Sorry, the trombone is smaller. So the basic construction of a brass instrument is as follows. Let's start with the valves. There are basically 3 valves, okay? And then we've got extras, but let's talk about the 3. The first valve, and I actually do not know the historical reason for this, the first valve opens up a length of tubing equivalent to 2 of the slide moves that Mark did. So 1, 2, and do just that distance is accomplished by the first valve. Doesn't matter where we are. You can play a few more. Doesn't matter where we are. When we push that first valve, we get that amount of lowering. When we push the second valve, you know what happens. That. And when we push the third valve, it's equivalent to the first plus the second. So anything that I can finger with the first and second, I can also finger with the third. Yep, and you see that the trombone is all done mechanically by lengthening, but think about this. If I push the second valve, I'm down. John, can you count steps, half steps for me? I push the second valve, I go down a half step. The first valve, I'm down another half step. 1 and 2, I'm down another. 1 and 2 is the same as 3. Now I can add 2 to 3, I'm down another half. Take up 2 and add 1, I'm down another half. And I add the second again, I'm down another. That equals?
6.
6 plus no valves at all equals 7. How many slide positions are there on the trombone? 7 positions. So we basically have created a situation with the valves where we're able to play all 7 positions that the trombone can play by combining our valves. It turns out that it's much more difficult to learn the slide positions than it is to push the valves. That's the easy part of playing these instruments, whereas doing the slide actually requires some finesse. Luckily, we have Mark Hetzler, who has that finesse in spades. Now, for the rest of the instrument, that's the valves. All of these instruments have a mouthpiece. Can you bring them over for a side by side? So you can readily tell the difference in size of the mouthpiece, and the size of the diameter of the tubing is likewise matches up very well. So the range that the instrument plays in is a combination of the length of the piping, but also the size of the diameter. So how long is the tuba?
About 18 feet.
About 18 feet. So this horn is, all told, about 30 feet of tubing, although I can't engage all 30 feet at once. But it's as much tubing as the tuba, but it doesn't play as low because the pipe is thinner. Now, when you add the mouthpiece and the valves, the only significant piece left is the bell. That part looks just like a bell. And the bell, I'm going to show you the way that it changes the sound in just a second. But inside here, there is nothing but a tunnel. There is no vibrating part at all. Probably if I wanted to do this, which I don't, but I had all of you come and try to make a sound, maybe about 1/3 of you could get a sound on the first try of this thing. It requires that the vibrating part be created in our own body. So if you think about the double reed of an oboe, it's 2 pieces of curved wood that are tied down together, and when you blow through it, those 2 pieces of wood vibrate against each other. The 2 pieces of wood, in my case, and John's case, and Mark's case, are our lips. And we have some skill. We could probably, if we wanted to, which we certainly don't, play a trio without the horns at all. And we could play probably a trio on our mouthpieces. We did not plan that, but that was good. So horns are just hollow tubes of changeable length. Okay? Now, what about when you take the bell off? This is ill-advised because this screw mechanism on this bell is hard to get back on, but I'll do it anyway. So here it is without the bell. So the bell actually has a big transformation on the sound. Now, I am not a historian of brass instruments or of science. I'm merely a student of my science colleagues, but I would surmise that this was not discovered through theory, but through experimentation until the sound met a certain standard that the musicians wanted to hear. I'll put this on in a minute. I brought a couple of other horns as well as a cornet with me that I want to show you. Horns can be made out of different materials. And they're made out of brass, but then they're plated in different ways. And we have a lore, so we say that the silver horns, which don't have any silver in them, they have a nickel plating, but the nickel-silver horns reputedly play brighter, and the brass-colored horns reputedly play darker. These kinds of things are very hard to test because it's extremely difficult to control the experiment. I cannot make the same exact sound every single time I play. There's too many moving parts. It's my body that's making the sound. So when a musician is testing an instrument to see which one he or she likes best, it's not a matter of playing it once and saying, oh, this one sounds better. You have to live with this instrument and figure out if it fits with the way you play. But I want to do a little side-by-side comparison of these two instruments. And by the way, the brass-colored one, which I'll play second, is a German handmade horn. Handmade not meaning there's a guy with a hammer necessarily, but there's a guy with a machine anyway, using some old-fashioned processes and making sure that everything fits extremely tightly. So the valve is in a casing. It has to fit with a very low tolerance. It's very tightly fits in there. And the silver-colored horn is an absolute piece of junk. I love the way it plays, but the valves fit badly. They click. You'll probably hear that a little bit. It has a plastic connecting piece that's going to break one day in a concert. But we'll see if they sound different. I haven't really done a side-by-side comparison in front of an audience, so we'll see what we think. So here's the silver American-made junk that I like. And the German nice horn. Now, if I asked you, describe the difference in sound. Who heard a difference in the sound? There's a pretty big difference in the sound. So if I asked the gentleman in the back, he might say, oh, the German one is darker. And then the woman in the white shirt here might say, the German one is brighter. It's very hard to describe sound in any kind of meaningful way. But we can say, well, they're certainly different, and they feel a little bit different to play. I want to show you, before we play our piece, I want to show you also this cornet. I don't play the cornet or the trumpet, but I'll show you that the instruments are similar enough that I can play it badly. And this is an instrument that I bought at a flea market for $100, and but it's beautiful to look at. I'm guessing that it's maybe 80 or 90 years old. It smells like a brass instrument, so if any of you were in band in elementary school, the smell of this thing would be very familiar to you, very evocative. And I just want to show you also that the valve combinations are exactly the same. The second valve lowers at a half step. First valve, a whole step. 1 and 2 is a step and a half, and so is 3. Our trumpet professor would be appalled that I did that in public. But so you can hear the different sound. Now, there's a certain similarity between the sound of the trumpet and the sound of the trombone, although not when you compare these particular two players. But the large majority of the length of the piping on the trumpet and the trombone is made out of cylindrical piping, whereas the horn and the tuba, the piping grows and grows and grows and grows and is therefore called conical piping. And the effect in the sound world of the two different kinds is that there's, well, here I go with words, right? But a brighter sound, more martial sound, a sound that cuts, I don't know what you would want to call it, on these instruments, and a more mellow, round, beautiful sound. Definitely a more broader kind of a sound on these instruments that are the horn and the tuba. So I'm going to move the table, try to get my bell back on. The next, as I said, my colleagues are the trombone professor, Mark Hetzler, and John Stevens, our tuba professor. I want to mention also that John is retiring in a couple of days. And so it's a really, really great honor for us to get to play this last time with him for you. And he's an extremely distinguished member of the faculty, and so we're going to miss him very much. He wrote the piece that we're going to play for you. He's a prolific composer, especially of music for brass. And as I get myself set up, John is going to tell you a little bit about the piece. And then we'll do a few little examples for you, and then we'll play and get you out of here.
Thanks, Dan. Before I came to Madison in 1985, with a little hiatus of 4 years teaching at the University of Miami in Florida, I was a freelance performer in New York City. And I played in, among other things, a brass quintet called Pentagon with various players from the Metropolitan Opera and New York Philharmonic, et cetera. And we were preparing a debut performance in Carnegie Recital Hall for the quintet in 1978. And it became apparent that this was going to be a very strenuous program. One thing Dan didn't say is that playing these brass instruments, while it's an artistic endeavor, is also rather an athletic endeavor. It involves muscles. And as you might imagine, the larger the mouthpiece, the muscles are involved in a slightly different way than the smaller mouthpieces, such as horn and trumpet. Typically, the literature that we play is a little bit more taxing for trumpet players, for example, than it is for low brass players. So what was happening is we were putting this program together, and the trumpet players were saying, boy, I just feel like we're going to need a rest in the middle of this program. So I volunteered to compose a piece for the lower three brass players, horn, trombone, and tuba, in order to give the trumpet some rest. Now, just to give you an idea of what I'm talking about, right now, almost everybody in this room has on your face what I would call a regular look. You're not smiling, you're not frowning, it's just regular, right? Probably the first look you have on your face in the morning when you look in the mirror before you go, like if you're like me. So this is not a particularly strenuous thing to do. That's why we have this look on our face all the time. Now, pretend you're a little kid and you're visiting Aunt Gladys and you have to give her a kiss. All right? Imagine holding that for 15 minutes. Okay? This is kind of what it's like to play the trumpet. No wonder they're kind of crazy. So they need a little bit more rest than we do. So I composed this work called Triangles. I called it Triangles because it's written for 3 instruments, and it's a through composed piece, but it's in 4 different sections. So I thought, you know, I think maybe because the group was called Pentagon, I was thinking in terms of shape, and I decided to call the piece Triangles, and that's what we're going to perform for you this evening.
Okay, so we just want to play a few examples, get you to get your ears attuned a little and get a little warm up in on the side here before we play the piece. So we're going to start with the opening, in which you will see the power that these instruments can muster, as well as the transformation of sound from that kind of power to a much softer and gentler approach.
Hey, Dan, can I just mention one thing about the opening bar, which might give them something to listen to? The very opening of this piece, the 3 of us are playing in unison. We're all playing the same notes. You could play it with 1 finger on the piano. What this means, given the different sizes of our instruments, is Dan is rather in what we would think of as his lower register, and Mark is in his middle register, and I'm in my upper register. And this same principle works for all the different families in the orchestra. If you write the same line for violins, violas, cello, and basses, for example, in the string section, it's going to put all of them in different registers of their instruments, which creates a different sort of intensity. Probably more than you wanted to know, but anyway, that's something to listen for.
The next section requires me to get my mute, which I forgot to do, so that's going to take me just a second. But you'll hear a very different character. One thing that's interesting about the brass family of instruments is that they play equally well classical music and jazz, and a lot of the music that John writes explores jazz sounds, and you'll hear a sort of a jazz-influenced, although non-swing section here. And then for contrast, a also somewhat commercial sounding section, but with a very, very different character. So with that, I think we're feeling ready to go. Thank you so much for coming. For the repeat customers, thanks for sticking with SoundWaves. We love seeing you every time. This guy's unbelievable. So is that guy. They're here every time. It's really a pleasure getting these scientists speaking for all of us. They're brilliant, and we learn so much. Please feel free to come up and chat with us when we're done. Here's Triangles by John Stevens.